So today we have three speakers, three different companies, two different technologies to talk about the underlying memory technology. It's also kind of interesting that this used to be the first session in the morning of Persistent Memory Summit, and it's kind of good that it got moved to the afternoon. We might say there's less focus, but that also means that more and more applications are being built on persistent memory. So that's certainly one good way to look at it. Andy Rudolph did a fantastic job this morning of defining what persistent memory is. I refer you back to his definition. And the two technologies that these three speakers are going to be talking about are MRAM and RRAM. We did hear a very good presentation this morning, the first presentation from Intel about 3D Crosspoint. One of the things that Intel consistently stresses, especially in the SNIA forum, is hey, other memory technologies can do the job or some part of the job of persistent memory as well. So first speaker up will be Danny Sabour from Avalanche Technology. Let's give a round of applause to Danny.
Is there a clicker, a microphone? Hi. I'm Danny Sabour. I'm from Avalanche Technology. I'm going to talk about some of the memory products we're working on and where they fit in. I did a presentation in the last year with Dave and company, and we went through the markets. And this is more of a product focus by the time we get into it. I use a generic foil to describe the markets we're going into. It's the whole infrastructure all the way from the IoT node to the edge to the cloud. There are products being developed at all layers, and persistent memory comes into play in every aspect of the system. The IoT node is collecting data, working on it, sometimes manipulating and sending back, sends it to the edge, some form of edge. We work on the data at that point, we retransmit it to other domains, and then we send it back to the cloud. This whole thing has been going on for the last 5 years. There are more devices being added to the IoT infrastructure. Persistent memory, the role it plays is you reduce your power consumption, and with all the machine learning and that we have today, it's becoming more intelligent. The main aim is to reduce the data flow between each layer. The microprocessor companies have done a great job. Intel, ARM, some others are doing a great job in the processing side of it. We have enough memory in the systems at the cloud and the edge. And what's coming into play is persistence. Again, everybody's talking about persistence and what role that plays. Given this picture, we're familiar with it, I think. Next door, they're doing the machine learning and artificial intelligence. We run the training in the cloud, and then it comes back to the node, and the node does the inference. What happens in the node is we collect the data, we aggregate it, and we send it back to the edge. This has historically been happening for the last few years. We started to fuse the data to reduce the data flow, and sometimes we configure it. The key things here are persistence, low power, and smaller size. This is what new memory technology is giving us. And the latest buzzword for the last 2 years has been machine learning. So what we do is we add local decision making to reduce the amount of data being flown back. Sometimes you don't have a connection and you have to do it locally. So this is actually our roadmap, but I think other companies have a similar roadmap. I'm going to come back to is the technology. MRAM has been referred to as one technology, but besides it being one technology, it's many products. And I think that's been not addressed over the last couple of years when we talk about MRAM. As you look at it as a technology node, we built a perpendicular MTJ stack. We have numerous versions of this which build different products. So although I have a perpendicular MTJ, I have 3 different product lines. In the IoT space, I have what are called discrete memories for IoT. These are external memories. We have 8 megabits. We have 32 megabits today. And I'm building a 256 megabits with faster interfaces. These are external memories that traditionally were taken by the NOR and some external memories. The product I'm building today addresses those needs. What it does have is low power, and with an IoT node, you want to power it down and move on to the next phase. This is only part of the solution. When you come to IoT and integration, you have to go for lowest cost. So what I'm doing is, as an embedded memory, I'm doing macros at the foundries. The next generation is 28 nanometer / 22. I'm building 2 different macros. One is an SRAM macro, and one is a non-volatile macro. Again, these are 2 different products. They have different behaviors, and they basically replace the SRAM and the NOR in an IoT device. Moving on, I don't need to upgrade the non-volatile memory, but I do need to upgrade the SRAM functionality, so I'll upgrade that functionality with new products. That's what's happening at the foundries. We work with one foundry. All the other foundries have similar products and roadmaps. We come to the edge and the cloud, and we discussed this. Basically, it's a PC architecture. The CPU has lots of DRAM, lots of cores, and in some cases, we add a multi-core from NVIDIA or Intel in there to do your trainings. We add a PCI cache, and we add extra caches to the storage subsystem to speed things up. Many companies are providing these solutions. What you need is, again, persistence and speed. We're doing the learning capabilities here. Where we add performance is in the form of a PCI cache. MRAM comes into play here because it's very fast compared to a NAND structure. We have a typical PCIe interface, enough MRAM to be the front level cache behind the NAND structure and the rest of the subsystem. The GPUs, I'm sure you've seen the presentations again. They need persistent memory, and what we do as a function is we provide the persistent memory for the coefficients. What I call these are, I call them medium density persistent RAM. And I'll come to the roadmap in a second. This is really 1 to 8 gigabits. So this is a phased approach to memory introduction. Each memory density has a different function here. Then we get into the next part, which has been historically the NVDIMM-N with a controller, battery, and flash. Again, architecture is well known. Power fails, we copy the RAM into flash. When power comes back, copy the flash into RAM. New generation is coming, NVDIMM-P. Again, other presenters have spoken about it. Use a controller to hide the write cycle of the persistent memories that are coming from other manufacturers. What we do is, with MRAM, our promise is, because of its symmetrical nature, we don't have the same write cycles, so we pretty much perform at DDR speed. And I call these high density persistent RAM. Densities go up from 8 to 64 gigabits. Now, as a company, what do we do? The bottom technology section is showing 2 different rows. The one with what I call regular and small, these are transistor-based switches. So these shrink at the same geometry as your normal process shrinks. So we go at 28, 22, and 14 nanometer. With those transistor shrinks and the MTJ itself shrinking, we're looking at today at 35F squared going down to 20F squared, and that gives me a density of initially at 22 nanometer up to 4 gigabits. That density goes up and I can, by reducing the size of the cell and everything else, I can take it up to 16 gigabits by stacking it. That's what I call medium density. I'm not addressing the DIMM space with this one, but I'm addressing what goes into the storage devices and the PCI Express accelerators. In order to get to really high density, we have to replace the transistor with that yellow and pink structure, which is referred to as a bidirectional diode. It doesn't have the same performance characteristics of a transistor, so you have your reduced endurance. Now, again, this is a different product, and the whole structure shrinks. By shrinking it, I go to 8 to 32 gigabits and going up to 64 gigabit. Now, I call that one my high density and mid density memory roadmap. I'll put this slide up. This has appeared over the last 5 years in many different formats. Every company has done their own spin on it. I think what's missing is it needs a couple of more dimensions before it makes sense. But we have a magnetic structure, and I generate products with our magnetic structures in different formats. I have an ESRAM structure, which has the endurance that we want to go into an IoT device. I have an eNVM structure, which has the ability to withstand reflows at high temperature. It's a different product. And then I have a standalone device which acts as data loggers. This is where FRAM and non-volatile SRAM has been working. 3 different products. They're all based on MRAM. And then I add medium density and high density DRAM to the roadmap. Again, different products. This is not just to say there's NOR and it fits there. MRAM fits in many different places, and software and hardware will be unified using this structure. I have also put the spec on our website in case people want to go look at it. So we're making inroads into devices all the way from IoT to the cloud. We are driven by a software-defined network today, which unifies us all the way from the network to storage and cloud, similar architectures, and product introductions has begun.
All right, let's thank Danny. Next up will be our speaker, Kevin Conley from Everspin Technology, a company that's been a pioneer in MRAM. And we'll bring up your presentation, Kevin, and get you going in just a minute. Please hold your questions till the end.
And Kevin, you can wear the lavalier if you want to walk around. So if you want to move away from the podium, you can put the lavalier mic on.
That's okay. Okay, don't worry about it.
All right, so I think our view of where MRAM plays in the ecosystem is fairly similar to what my friend Danny here just showed you, in terms of looking at from the core to the edge and all the way to the devices at the in the IoT sphere. So just kind of moving through that, the 3 stages of that, we'll focus on more on the applications. Everspin today is playing in a lot of these and working on MRAM adoption into many of these. So at the core, it's all about acceleration of data in the data center, anywhere where persistence is necessary because of the value of that data, the cost of recovery of that data if it's lost during power fail. We see this in enterprise SSDs and all-flash arrays today, the biggest consumer of MRAM in the data center, as well as in RAID controllers. And then we see storage accelerators, which are introduced into servers as part of a standard storage stack, with the capability of a lot of the RDMA features you heard earlier. And the newest trend in here is looking at persistent NICs and how MRAM will be able to add the ability of persistent memory to network adapters as well. If we look at of course, the data center not just being the only place where data is relevant. As we look at the 125 zettabytes that are supposed to be consumed and generated in 2021, 75% of that is going, or 2025 is going to be outside the data center. It's going to be at those edge gateways and out in the IoT devices themselves. A couple of examples, and one of our most interesting that we're coming across lately is in network video recorders, where you have hundreds of streams of video data, high density video data coming into these video recorders that need to perform analytics on that data and make inferences, and those inferences are incredibly valuable, cannot be lost in a number of different applications in consumer and industrial. And as well as at the edge, today MRAM is already playing a role in many of these devices. In the past, a lot of the technology that we've been producing in the first generation MRAM was adopted into things like casino gaming, auto, industrial, infrastructure, PLCs for smart factories, all these places where the use of batteries, capacitors, is just not acceptable in a lot of these applications, either because of reliability, concerns with having chemical-based power storage. A real persistent memory is needed in densities where MRAM has been serving. Quite different than some of the server applications of persistent memory that have been discussed earlier today. But this is where MRAM has been, and now is being adopted in a new wave of embodiments in SoC. So as the controllers and the devices that run these applications are shrinking and becoming higher integrated with a combination of compute, memory, wireless, going into SoCs at advanced nodes of 28, 22, and below, you're already starting to see MRAM replacing NOR flash in these, much as what Danny was talking about. So MRAM has been playing a strong role here and is going to continue for the foreseeable future. Now, why is that? The persistence, the performance, endurance, and reliability, these are things that it delivers at a way that no other memory technology does. And this is something that I'm not going to go into a lot today, but for those of you that are more technical, want to understand where MRAM has been and is going, it's been in a lot of industrial extended temperature applications in the toggle MRAM, and now as STT, which is coming out of, I think in past persistent memory summits been really talked about as something that's coming, STT is now here and it's in mass production. So that's where I'm going to focus a little bit now. So I think Danny and I tend to see the world on the same two axes in terms of latency and endurance, so he spent a good amount of time going over this. We talk about persistent memory in many different applications, and we like to distinguish the persistent memory of MRAM from the applications that normally ReRAM and CBRAM and 3D crosspoint address in storage class memories, where instead of trying to be something that's faster than NAND and cheaper than DRAM, we're actually looking at trying to bring persistence into the true memory latency and endurance areas where we can handle the workloads that are required by these memories, which is obviously something that is still ways away for other technologies. And so today, we just recently announced that 1 gigabit is now being sampled to customers. This is the first gigabit class memory which actually meets all the endurance, persistence, reliability requirements that are required for this, and actually going into the integration now into end products. So it's a new era for MRAM, and just the beginning of its wider adoption. Now, to understand why MRAM at these kind of densities is adding value to this, because as we've not been shy about, MRAM as an emerging technology on a bit basis is more expensive than DRAM, but it brings things that no other memory technology brings in terms of the ability of devices to have a safe place to put high performance data that's protected from the time it's written and doesn't require battery backup. Why is that affordable for IBM, for example, in their all-flash array? It's because they're able to take the place that normally capacitors would be used for, replace that with flash, and produce the highest density storage module in the industry with almost 20 terabytes. They're able to deliver the performance required because it's using TLC flash, and with those slower, higher density memories, you need a place to build up bigger buffers of data in order to optimize all the storage streams that are coming down to these devices. So this is something that MRAM does uniquely, and another key factor in here is that the innovation built into the device level really needed to have a different architecture that only MRAM could support due to the fact that these are based on Xilinx FPGAs, which of course is one of our key focal points for early integration of these devices. Similar in storage accelerators, which are also available in the market. Today, these are going into servers, initially focusing on things like fintech, where the logging of transactions requires a persistent memory, very high value associated with these transactions, and other solutions just don't fit the bill in terms of offering a standard NVMe device with no latency tail. These are consistent 100% because they are read-write like DRAM, not unpredictable in terms of latency like other storage medium. So these are very interesting applications where MRAM is uniquely positioned. Fabric accelerators is a new one coming, as I talked earlier, looking at networks, looking at NVMe over fabrics, and the need for data in flight now to be persistent in order to be able to acknowledge earlier in the transfer of data, cut down network and storage latencies in a way. Again, no ability to rely on capacitor-backed DRAM for these type of applications, and looking at the physical footprint of these and the power requirements, unique opportunities for STT-MRAM in these. A couple other applications for toggle MRAM, which is the legacy stuff, which are still being adopted into new applications. And if you hear a common theme in these applications, it's where that data in things like the capturing of transactions in gaming machines, not your typical places where you think of persistent memory, but that's where it started its adoption, and it's moving up the technology curve. So in terms of what's coming in MRAM, MRAM is no longer a future technology, it's a current technology. But as we look at that we'll see more discrete MRAM expanding in the adoption of data center and networking applications. You'll see growth of discrete MRAM in mission-critical applications such as gaming, industrial, transportation, medical endpoints. It's going into health wearables. It's going into mission-critical controls in automobiles and other types of aircraft. And lastly, you're going to see MRAM being adopted into SoCs in consumer, industrial, and other transportation endpoints in embedded format. So thank you very much for your attention today. Very happy to and looking forward to your questions about MRAM and the other technologies.
All right, let's thank Kevin. Very good. And then our third speaker is Keiichi Tsutsui. He goes by Amigo, which is much easier to remember. And he leads an effort at Sony on a technology that they call ARAM, but you'd probably consider a resistive RAM technology, and he's going to speak about that now.
Thank you very much. Thank you, David. From Sony, I'm Amigo. Please call me Amigo. From capacity and the performance point of view, the real persistent memory, chip level, is only Intel Optane now, actually. Do you need a second source? No? I hope so. And today, I talk about a candidate technology, cross-point RRAM. This is comparison between the PCM technology and RRAM. Intel Optane based on the PCM. PCM based on the thermal operation, So reset amorphous state, set crystalline. So you can see the amorphous case, reset pulse is a very high current. So that means over 100 microampere power barrier existed. And also set pulse to make a crystalline, little by little, we need make a crystalline. So that means performance barrier. So set time over, average is over 500 nanosecond. On the other hand, the RRAM operation mode based on the electronic switching. Electronic switching, so that means low resistivity, high resistivity, very high speed switching is possible. Current around 50 microampere, and also set reset pulse lower than 100 nanosecond. This shows we demonstrated 10 years ago in IDM, this paper. We demonstrated our RRAM technology. Set pulse 5 nanosecond, reset pulse 1 nanosecond. But in this case, we used over 100 microampere. In that case, very high speed we can achieve, we can show, we demonstrated. And so cycle is 1 megacycle, and also retention is 10 years is possible. Today, we are developing a cross-point type RRAM. So very similar inter-obtained structure, cross-point. So word line, we use so red material is RRAM, originally same material. And also blue is so selector, our original Sony selector material. This shows a cross-point structure. The different, very different from the PCM crosspoint and RRAM crosspoint, our RRAM crosspoint structure. So that means, so PCM case, unipolar operation, but our case is a bipolar operation. So we use a set and read positive bias. So you can see selected cell, memory cell, word line, we used half V set or V read bias. And bit line, negative half V set or half V read bias. And so that means only just one memory cell, cross-point cell selected. And that means same word line memory cell and bit line memory cell is a half bias is given the half bias, half voltage, and we need also a low leakage current in half voltage. And also reset is reverse voltage we need, and minus word line has minus half bias and bit line positive half bias. This is different from the PCM crosspoint. 2 years ago, we demonstrated VLSI Symposium 100 gigabit class crosspoint RRAM technology. So you can see the left side selector characteristics. So in half voltage, leakage current almost zero, and also cross section like that, kappa RRAM, and also selector technology. And transient pulse, set pulse less than 10, about 10 nanosecond, and reset pulse also 10 nanosecond. We demonstrated. And so we assumed now designing for the possible performance. Cross-point RRAM target, page size, sector size, access size, 500 terabyte, and read throughput 3.2 gigabyte per second, and read latency 0.4 microsecond, write 1.2 gigabyte per second, and also write latency 2 microsecond. Write, including pre-read, need also likely 0.4 microsecond, plus set pulse and reset pulse, after that verification. So four operation mode, including for the write latency. And on the other hand, our issue is controller technology. So now we use some controller technology, we assume. So ECC, we are labeling also need a special control technique to manage, compensate selector characteristics and memory characteristics. 1 microsecond latency. So cross-point RRAM plus controller latency, so you can see read case is 1.4 microsecond. Write latency is degraded, so reduce ECC time 2.4 microsecond. So that means controller technology very important for us in compatible with memory technology, memory latency. So we assume 8-chip target, 8-chip case, read-write size 4K byte, read throughput to 25 gigabyte per second. And read latency almost same, 1.4 microsecond, write throughput 9.6 gigabyte per second, and write latency also same as 2.4 microsecond. We assume that. Now is designing and developing. And so this utilized to the EDSF short type form factor. So you can see we assume that the PCI Gen 5, in that case, a very high speed. If the controller consumes 5 watt plus RRAM chip, one chip consumes 1.2 watt. In that case, total in 8 chips case, neither 14.6 watt. This is exceed over the EDSF short power consumption standardization. So that means RRAM power is less than PCM, but bigger than DRAM. Need to reduce the power of RRAM plus controller technology, very important to reduce the power. So high performance consumes high power. So we have to care for the controller technology. Summary, cross-point RRAM is expected to high performance application such as persistent memory. The power consumption must be considered for small form factor application. The dedicated control design is also needed to reduce the total power. Thank you very much for your attention.
Okay, now it's time for your questions. Hold on, Kevin, hold on. Kevin's always has a good question, but we'll get to it in a bit, and I see a Neil. But I want to start first by asking my question and to give you some warm-up. So for each of you guys, and let's start for both Danny and Kevin, because you have a shipping technology. I want you to put a fine point on what is the major product and market focus for your company in 2019. Amigo will say 2021 for you, not so soon. But go ahead, Danny. What's the main focus for Avalanche in 2019, product and market?
So we're starting with our discrete product lines. I don't have the high densities that Everspin has in 2019. I'll be sampling what is shipping today. I will address the embedded market, standalone logging markets, and I will sample the mid-density RAM in 19.
Got it. Kevin, 2019, major focus.
So We have a couple major focuses. We have the majority of our revenue today coming from industrial markets, and we'll continue to see those expand. The STT is the fast growth driver, and today it's in data center acceleration, mostly in all-flash arrays, where we see that, as well as we expect the productization in other SoC embedded applications to happen this year.
Okay, Amigo, let's give you a couple more years. 2021, major focus for product and market.
No. We accelerated 2020. So.
Okay,
Yeah.
so he just pulled in his schedule by a year. Okay, Amigo, 2020, major product and market focus for your technology.
Yeah, so I already explained about that. That's I follow the Intel Optane solution. So customer needs a second solution, right?
Second
So,
solution, not
yeah,
beginning with an I.
Yeah, to expand a new architecture. So DRAM and NAND. So between the DRAM and NAND solution, customer need.
Okay, very good. Now let's open the floor for questions. I saw at least 3 hands go up. Do we have a microphone out there? Marty, yeah, let's go ahead and start with Kevin. So Kevin is a frequent attendee to FMS and the RRAM and MRAM sessions and always throws us for a bit of a curveball. Kevin, what do you have for us today?
Okay, so I have 3 questions, 2 questions. Oh, sorry.
Oh, please identify yourself and your company.
Kevin
Thank you.
Bracey Computer Laboratory. So, okay, since I only have to do 1 question, then I will limit to 1 question. This is a little hard question, and if you feel like this is kind of harsh or, I don't mean to be offensive, but I think we have to kind of tolerate sometimes.
That's
hard
okay. We
questions.
already had harsh and offensive this morning for the Intel speaker. I thought it was quite harsh and offensive, but okay, go ahead.
So, one thing I always wonder about, non-flash, NAND flash, non-volatile memory, is that there never seems to be what I call a roadmap to get out the niche status.
Mm-hmm.
And the reason why this is a very important philosophical argument is that the inventor of NAND flash, Dr. Fujio Masaoka, he's about 76 years old now. One of the things he observed.
Okay, Kevin, get to the question. Okay,
one of the things he
Let's
observed when he came up with the NAND flash idea was cost is everything in the memory business.
Got it.
And one thing I don't see with MRAM or ReRAM or PCM 3D Crosspoint is how do you get out of the couple $100 million niche to become multi-billion, tens of billions of dollars like NAND flash has become?
Great question. You must have been reading Jim Handy's blog here in the last few days, right there. Okay, so dollars per gigabyte is often a measure for success or failure in the memory business. How do you answer that? Go.
All right. So we used to get that question a lot back in 1993 when I was working at SanDisk and SunDisk at the time, where we were being asked, well, when I don't believe Flash can ever get out of this niche category, when are you going to challenge hard disk drives? And, you're hundreds of times more expensive. When is it going to be there? And there is a focus on cost, but every technology goes through waves of integration, of expansion, of scale of manufacturing. So it's hard maybe for you to see how that works over several generations and several years. But today, I pointed out MRAM's already adopted into a wide variety of gaming machines and transportation and industrial applications, which is exactly where SanDisk was selling flash back in 1993 to 1995 before the digital camera came out, right? So we're now going into SSDs. Why are we going in? Not because we're cheap like a DRAM. I'm not trying to be cheap like a DRAM. We go in because we offer something that a DRAM can't do, that you don't get a 19.7 terabyte storage module with 6 nines of consistent low latency under 100 microseconds in a U.2 without having an ability to buffer a lot of data and be able to manage the streams into slow TLC flash. And so what I'm just going to say is have a little longer vision, and it'll be there, don't worry.
Yeah, 1990, Ali Harari told us, yes, we do have 10 minutes, by the way. We're not cutting you off. We stole 10 minutes from Tom Coughlin and Jim Handy, who we know can talk for much more than their allotted time. So in 1990, El Harari, I remember saying that we're going to be successful when we're 1.5x the cost of hard disk drive. Now, NAND or other media never got to that. It's still much more expensive than that, but it's still been successful. Okay, next question, Anil Gupta. Please, I'm sorry, I introduced you, but name and company, thank you.
Okay, I'm Anil Gupta. I am with Winbond, and I've been in the floating gate since 1981 from SEEK. Many people are too young here probably to know SEEK. So anyway, my question is similar to his question, and I thought I'm going to retire with just floating gate and nothing else happening. You know, all these conferences and all these PowerPoints. So first I want to thank Kevin and Everspin. That's not going to be the case. I'm not going to retire with only floating gate as a real thing. I think the MRAM has become the real thing. But my question is, when does it change from a real thing to a mainstream, from a niche?
Okay, almost same kind of question, but I think
So
same kind of question from mainstream, from niche right now into more mainstream, or will it remain a niche? Danny, Amigo,
So can I just
care to?
comment on something?
He's not giving up.
Two
No,
parts.
Anil, I'm going to retire soon, you know? I mean, we only have so much time, my man.
Because one thing
Don't
about
grab the
going back
mic.
to here, Kevin, is the NAND was a 4F square. You do 2-bit per cell becomes 2F square. You do 3-bit or per cell becomes 1 or 1.5 F square, right? So that's one part of it. Because you didn't really talk about, and maybe you don't want to talk about proprietary, how many F square is.
No, I think we even heard that. We heard a mention from Danny.
We heard from Danny, but we didn't hear from.
Yeah, we heard from Danny. Danny, why don't you go ahead and talk about that, because
I originally started with an Avalanche page, and I changed the slides to say this is an industry page. The F squared, 35, 20, then 8. That's my roadmap, and it's anybody who's doing MRAM is doing the same thing. What's happening is, I think you're jumping so far ahead. Memory technologies take 10 years to mature. The equipment manufacturers, all the stuff that's going into the foundries are going in. They're stabilizing. We're getting to productization of quality products that are stable. You start at the high end and you drop the price. If you look at the first roadmap slide I had, I put the die sizes. If you look at the 3 die sizes, they're shrinking. The die size is shrinking. The processes are maturing. Everything is going according to plan. Memory takes a decade.
I think one of the interesting things too, Danny, maybe talk a little bit more about what you had on your slide. It was only a small mention, but Avalanche has presented a paper on driving instead of with a transistor, doing it with the diode, which could take MRAM into a cross-point structure, which is quite interesting. That would also scale the cell. Maybe elaborate on that a little bit more, and perhaps even the time frame of that.
It's okay, I can answer the question. So, like I said, the first step is mid-density up to 8 gigabits. This is where we're doing products to get there. They have the first generation already at 1 gigabit. In order to get to high density, that's a further 2 years out. So once this stuff becomes mainstream, the mid-density, then we start to tackle the next one. You can't just say, I'm going to go jump into that space.
Okay.
But I say the magnetics are working. And that's why with the magnetics working, now I can focus on the circuits.
I'll add one thing, because Ellie and I talked about MRAM back, I think it was 2008, at that time. And, the concern was, well, you got these 45F squared devices. These are never going to compute. But the interesting thing that I saw then was that, well, as you shrink the size of an MTJ, the power goes down. Now, there's a lot of things that have to happen to be able to enable that and still have data retention and endurance and these sort of things. But this is what Danny was alluding to, that the manufacturing capabilities are now getting huge investment in it because all the major foundries are driving MRAM. Now, once you have that happening, that gives you the ability to build more robust cells. Once they're more robust, you have less edge damage. You can shrink them. You can go to higher density, and you can start to get even higher density on today's technologies. You don't have to shrink the technology. So that's a key thing to understand. And the next thing is you have to have manufacturing scale, and there have to be multiple competitors in the market. So, I'm waiting for my friends at Avalanche to have another part out there so that really we can build a robust industry. And as Danny said, I think 10 years actually is a pretty optimistic thing. It took us 12 years to really, or 20 years to challenge hard drives using flash, right? So.
Yeah, no question. Okay, I think we have time for one more question. Alan, I saw you had your hand up earlier. Why don't you get the mic? Anybody else that wants to queue up a question? Alan's right in the middle here. And we'll come back to Ed over here. Please introduce yourself, Alan.
Alan Nebel from WebFeed Research. My question is directed to Amigo-san in terms of what kind of density are we looking at in 2020 that you're...
So 64 or 128 gigabit.
No, gigabit.
64, 128, what density? Gigabit?
Gigabit.
Gigabit. Okay, good. I'm glad you asked Amigo a question. He was getting off quite easy here. So I'll let you follow on that question with another little harder question. If you have one.
Well, I don't know if I do.
Actually, formal question I would like to ask.
Please, Amigo. Yes, thank you.
So in general, so actually, cost is most important, I think. But technology is also important. That means currently 3D NAND not use floating gate charge trap type, right? And so technology changing. So I invented a memory stick before the SD card 20 years ago. In that times, so no SD card, we used controller managed NAND and NOR, all types of non-volatile memory. That means in that times NAND was not cheapest solution. That we could use all kinds of the non-volatile memory. We had to use. So that means after that, NAND was successful. Why? That controller technology, I think. So Tanaka-san, Toshiba, he discussed about it with me. So 20 years ago, right?
Yeah. Another famous guy in the audience too. Very good.
And why? That controller technology very important to save the error of the NAND. And so please understand these kinds of the emerging memory technology has a potential, but nobody can look at the future application and the future memory technology.
Okay, let's try for one final question. Ed, please introduce yourself.
Thank you very much. Every year I hear this, we make more and more progress, so congratulations. There's one point that I'd like to bring up, and that is the word costs. Cost is like sin. Everybody knows about it, but nobody talks about it. There is a relationship between cost and area and scaling. And I have to tell you that to date, I think a lot of progress must be made to scale persistent and non-volatile memory. And one of the reasons for that is that specifically in the unit cell, you need a selector to prevent the area and also the current from going to the half select mode, okay? And the selector is an integral part of the unit cell in every one of the technologies, gentlemen. I haven't seen a lot of progress yet in defining that selector. Some in our RAM, some, okay? But I think we need more work there. And hopefully the next time this committee meets, okay, and Dave officiates, we'll hear more about the selector technology.
Okay, so we'll say that was the ending point, and I don't think we have. Okay, Kevin wants to respond.
I'm not sure that was a question.
There was not a question in there. I was waiting for it.
So I'll state my answer in the form of a question.
This is Jeopardy.
Bob,
I'll
that
take
would
selectors
be,
for 500, Alex.
What kind of memory doesn't require a selector? And that is the types of MRAMs that we're producing today, which means selectors haven't been a problem. If, of course, as you adopt MRAM technology into 3D cross-point arrays, if that's truly the path of integration, those problems will certainly come to the fore, but they haven't been an issue for us to date.
Okay, and then if you love this topic, please join us at FMS, where we'll certainly have an RRAM and MRAM panel, and it always proves lively. So let's give our presenters a round of applause for taking our tough questions. Thank you, gentlemen.
Very good. See, I wasn't kidding. We had persistent fun right there. That was good. All right, so speaking of fun, welcome to the Tom and Jim Show, starring Tom and Jim. That's right. That would be Tom Coughlin, who's president, El Presidente of Coughlin Associates.
Whoa.
And then Jim Handy, who is general director of Objective Analysis. Many of you know Tom and Jim.
So one of you.
They're well versed in the technology and stalwart industry analysts. So without further ado,